Okay, and this presentation is again one of the work of the Hexaphone project. Is going to work to show the work done with his colleagues on understanding superlinear speed up in current HPC architecture. Please, Flavio.
Thank you, Ivan, for the introduction. So my name is Flavio Galeazzo from HLRS. I present a work that was done in the Hexaphone project, and not me together, but our team, so with Gregor Weiss and Andreas Hoop. I will start with this introduction, then I will show results that we got with the Grand Challenge, and then I will move to the test case that I've used for this lead-driven cavity. That's boring, but I will show why I've used it, and then summarize the results. And in the context of the Hexaphone project, the strong scaling of OpenFOAM in various HPC architectures was analyzed, including AMD, ARM, and Intel systems. And we have seen some in some of these systems this pronounced superlinear speedup. We have also seen that in other presentations throughout the workshop. For example, with AMD EPYC processors, we can see linear speedups of order 300%. And this speedup has implications of for the efficiency use of the computing resources, and this led to these results that I'm presenting today. First, I will introduce the Grand Challenge. We had this talk from Sergey yesterday. It's one of the main contributions of the Hexaphone project. It's based on the experiments carried out by Severin in DLRR. It's a combustor based on recirculation stabilized jet flame concept, C-foam solver, and I will show the results with the largest grid, almost 500 million grid cells. And what we see is these are the results of the strong scaling. It's the same results that Sergey showed. And the orange line shows the speed up. Yeah, and we see that this speed up, it remains above the ideal line. The ideal line is not shown here, sorry. But we see that the orange line, that's with the improvements from the Hexaphone project, it remains super linear until the use of 30,000 processors. Yeah, and it was very unusual for us. Then we want to study why we have this so pronounced superlinear speedup. We know that OpenFOAM and safety applications in general are memory bound. The bottleneck is the memory bandwidth. As a result, the superlinear speedup is common when the available memory bandwidth increases when we use more nodes. But these benefits are diminished by the communication overhead when you use increasing number of nodes. And superlinear speed of about 10 or 20% is normally expected when you jump from 1 to 2 or 4 nodes, but normally we expect up from 4 or 8 nodes to not have this superlinear speed up anymore. But we have seen that we have this very pronounced speed up. Then why I use the cavity, solid cavity test case for that? Okay, again, so these modifications are from Sergey and Eric. Why? Yeah, it's one of the most basic and popular cases in OpenFOAM for the validation, also in the safety community. We have already scaling results available, but in this time, I have used it because it's very easy to scale up and down the grid. And I will test a lot of different grid sizes to show why we have this superlinear speedup. And here I'm showing the strong scaling of the cavity 3D in our Hawk supercomputer in Galeazzo using OpenFOAM 2212. And the orange line is ideal speedup, and the blue line shows the current speedup that we have. Then we see that It's I go from PCG. PCG, the very standard linear gravity case. And we see that we are still having superlinear speedup until that also the 256 nodes. There are 330,000 processors, and which is very unusual. Okay, we don't have a very good speed up from 128 to 256, but we're still superlinear. So these measurements were done in the Hawk supercomputer, where we have for each node 2 sockets with AMD EPYC processor. That's 2 times 64 cores. And we have DRAM at 308 gigabytes per second as bandwidth. That's good, but it's not the best. But the major feature that we have in this system is this hierarchical L3 cache configuration. We have a very large amount of L3 cache in this system compared to prior systems. And these chips are divided in what AMD calls CCX, and every 4 cores share an L3 cache of 16 megabyte. And each socket has 16 CCX. Then it's like we have a cluster in a socket. So every socket is composed of a different clusters of 4 processors with this L3 cache shared between them. And then my idea is, okay, I have to have to measure the performance of one compute node with different grid sizes to understand why, when I do this strong scaling test, I'm diminishing the grid size, why I'm getting so much performance difference. The problem is how to compare these results with different grid sizes. Then the solution is to derive a metric. So I have derived this VOPS metric, this finite volume solved per second. That's very trivial, the number of finite volumes of the grid divided by the time per time step in seconds. That's similar to this mega lattice updates per second that the lattice Boltzmann community uses, or throughput, or flops. And this, it depends on all parameters of the simulation: grid size, partition, and parallel efficiency, number of variables. But it can use to compare, also to compare different systems with using the same inputs. Okay, so maybe then I will show then FOPS, this performance metric for grids from ranging from 27 million elements down to 15,000 elements in the same, using the full node. And what we see is that when I'm having a very large grid, I'm completely memory bound. The performance of the system is limited by the memory access that I can get. And then when I start decreasing the grid size, this large L3 cache comes into play. Then I can fit more of my grid in the L3 cache, a higher fraction of the grid in my L3 cache, until I get here by about 8,000 grid elements per core. I got the sweet spot when I have the highest throughput in the system. But then I continue decreasing the grid size until some 100 grid elements per rank, and then the performance breakdowns again. And what is special in this system is that this difference in performance between the largest grid and the sweet spot is almost 5 times. And that's why we see the superlinear speedup in the system. We begin our strong scaling test with somewhere here, where a very large amount of grid elements per core. We are completely memory bound, and then we do this strong scaling test. The grid size per core gets smaller, and then we access regions of this graph with much higher performance. And then to understand why, so why we have this so large difference between the large grids and the sweet spot. Then I have used the L3 caches. So then I have built the L3, what I call L3 ratio is the ratio of the L3 cache misses divided by the L3 cache hits. At the sweet spot, we see that the L3 ratio is at minimum. That means that we have less access to the main memory. Then it confirms what normally we think happens, but now we have values to corroborate that. Unfortunately, this L3 ratio is not as accurate as I would like to have, because in the AMD's Zen 2 platforms, it does not differentiate between L3 cache counters from system and from users. That's a hardware feature from these AMD processors. The newer ones, Zen 3 and Zen 4, they have fixed that. I got these measurements using the perf, and they are for total hits and misses. Then it's not only the hits and misses of L3 cache for OpenFOAM, but from the whole system, including Linux. PAPI counters that's normally used for these metrics are not available for the L3 counters in the Zen 2 platform because of this hardware counters. But okay, we see now why we have highest performance at the sweet spot, but again, why the performance drops when I still continue decreasing the grid size. Then I measure the MPI ratio, or the fraction of the complete time spent in MPI communication. And that's the green line. And we see now the MPI ratio increases when the grid size decreases. Yeah, it was measured with MPIP. And it's because the latency of the MPI gets, so the time per time step decreases a lot when we have a very small grid. And then the latency of the MPI plays a larger role. And then we see that when we have a grid of around 100 grid elements per core, we are spending so almost 90% of the time MPI communications inside one node. There's no communication between nodes. It's inside this inside one node. It should be fast. It's fast. It's shared memory because of the MPI, but no, it uses shared memory, but we still have a bit delay, and then this delay hurts. We can see here in the table that the time per time step is very, very small. It's 7 milliseconds. The time per time step by the smallest grid, and then the MPI delay, it's on the same order of magnitude, and then we get this large overhead. But I said that's HPC architectures, not AMD things. And then have also have done the same measurements using different hardware. We have then access, here we have the Hawk, and we have Vulkan, that's a smaller cluster, Galeazzo with Intel Xeon Gold processors. And we have access to the E4 partner from Hexafoam, where I could run also with two different, so one ARM processor, this Cavium Thunder X2, another flavor of AMD EPIC chip, and two different Intel processors. Disclaimer here, all these chips are between 2 and 3 years old. They are not so very up to date. But we see here that, okay, the Hawk has the highest throughput, the highest FOPS per node. But we see that all other architectures, they have more or less the same, they show the same trend that when you have the largest grid size, you're memory bound, and then almost all architectures perform the same. But then because of this large L3 cache from the AMD systems, we have a better performance here. And we see that for almost all platforms, the sweet spot is between around 10,000 grids per core, grid elements per core. Only this AMD system from E4, where the sweet spot is with larger grids. Then the summary is that the difference in performance explains these large superlinear speedups that we have seen in the strong scaling tests. And we have analyzed, so these systems use AMD, ARM, and Intel processors. And for the majority of the systems, the peak performance is when we employ around 10,000 grid elements per core. Furthermore, we can use, as CFD users, this FOPS metric as a simple benchmark to determine the optimal number of grid elements per compute core at any specific HPC architecture, and also for your specific test cases. Yeah, that's it. And using the system in the most efficient spot, what can it can give us saving not only in time but also energy consumption and also cost when you go to, for example, to pay for AWS instances, for example. Then, only to conclude, before the conclusion, I want to use this time to make two small announcements that we will host the second HexaFoam Summer School in Stuttgart this summer in September, and it will be a physical meeting at GLRS. And please access the HexaFoam website where you can find all the details for that. And also the benchmarks, the Grand Challenge, and also these benchmarks, lead-driven cavity, they're all available in the HPC Technical Committee repository. You can find the links for that also in the HexaFoam website. Thank you.
Thank you, Flavio. So let's say the guideline for the users is to try to calculate this parameter according to his architecture and test cases.
Exactly. My recommendation would be to test your test case in your architecture in one node, varying the grid size, and building this metric, you can see where the optimal number of grid elements per core that's better for you in your system.
It seems that is mainly dependent by R3 cache, mainly. This is by the cache. Mainly, I've seen the big difference between Oak and the other is of course the memory bandwidth and the R3 cache.
Exactly. So I wanted to also build this graph of this roofline model that we see that where we are memory bandwidth bound or compute bound. I couldn't do it with this AMD because I need access to some counters to calculate the flops. Yeah. So yeah. But my feeling then I didn't plot the graph, but we are moving from, so when we go to sweet spot, we move from the very memory bound to more compute bound, because then we have less memory access and then the memory bandwidth plays a lesser role.
Yeah, correct. Yeah, that could be a very interesting stuff to see in the roof line. Yeah, just a couple of comments. In past, try just to alleviate this issue when we have few years ago cluster with very low memory bandwidth. To decrease the superlinear speed up, we use less core than all the core in the node. Let's say if we have 48 core, we use 44 or 42 because let's say we increase the memory bandwidth per core in pass. And second comment, it could be very interesting to put your result in the POP metrics by Marta MBSC.
I have also these results here for the POP metric, but For the sake of time, I haven't shown that, but it's nice.
Yeah.
Hi, thank you for the presentation and great talk. Just a quick question. You said that the L3 cache can work in either private or shared mode. Have you tried both modes and see the difference between them? Okay, so you have no control over it, you said.
Could you please repeat the four?
Yeah, that's exactly for this Zen 2 platform. We don't have in the Linux kernel the differentiation in the of the counters for L3 user and system, but in the newer architectures we have. So then I'm trying to get access to a newer AMD platform to try to do it, but let's say. Yeah, so the question for Charlie is, if we have more L3 cache, what will happen with this curve? No, it will not be up, it will be larger. So we will extend the sweet spot to larger grid sizes. And no, only for the largest part. And for example, if you have these new chips with high bandwidth memory, yeah, and what we will have is that we will shift this tail here, so up, yeah. So no, up. So this tail here, that's where you are memory bound. For example, if you duplicate the memory bandwidth, you should have double the performance here, and then you have 3 times the memory bandwidth. You should have 3 times here, and then you have more flattened. The flattened profile as we had in the past with the prior generations of Intel or AMD chips. Yeah, you got more flattened because you have some different ratio of L3 cache.
That's a common pattern. I mean, this is a very common pattern in all memory bandwidth limited applications, because in AMD CPUs, the L3 bandwidth is super fast. It's around 800 megabytes, almost a terabyte. That's what this is what you're looking at. That's almost 1 terabyte transfer. But it's only because from L3 down, it's so fast.
I remember that the new Intel chips had a huge L3 cache, huge. Yeah. As well, the bandwidth is huge.
Yeah, we want both. We want so large size, large bandwidth. We want everything.
So the question was looking at this graph. So L3 cache on the Hawk is 256 divided over 128. And on the Armida AMD, the fourth one, it's 128 over 32, which is 4 per thing. No, next one down. That's the thumbnail you're looking at. Okay, sorry. So the next one down. So that one, another one's called, that's AMD Epic, yeah. So 128 divided by 32 is 4 megabytes, so it's twice as good as Hawk. But it looks way worse.
Okay, any more questions? Okay, thanks again, Flavio. Okay, first to move to the next last presentation, I would like to just Mark. Yes, please. Show you very briefly some update in terms of performance and tuning and guidelines. So we are talking about what is important to have a guideline, tuning, and documentation. And then Mark is working for us. Please, Mark.
Okay, this isn't a presentation as much as a request. Well, I still have a bit of a captive audience. Yeah, okay, a bit of a captive audience. As part of the exafoam, we'll be looking at communication patterns. One of the things we're looking at or dealing with is using non-blocking consensus exchange instead of an all-to-all. And this is used in map distribute power and in P streams. At the moment, this is set up on debug switches, which are all turned off. So 2306 behaves exactly like all previous versions. However, if you come in and you turn on the non-blocking exchange size to like a value of 123, you'll now use non-blocking exchange instead of an all-to-all for your size exchanges. Separately, you can do this in the P-stream buffers tuning, go from the -1 default to a 0, and that'll again use the non-blocking exchange for doing size exchanges. Flavio is gone already? No, okay, the first tests with a prototype from this prototype showed that it was like, I call it a 0-1. With the NBX thing, it was running on 8,000 cores. With the old scheme, it was not running. So very much a zero binary sort of thing. With the NBX, there's also some reports that to get everything synchronized, you may need a barrier at the front. So there's a special tuning parameter there. So read the documentation on the wiki. Please give it a try, report problems, successes, whatever, because we got to get it tested with lots and lots of people, and you are the people for doing that. Thanks. That's it. Thank you for this advertising.
Thanks, Mark. So there is no result published for the moment, no?
Now settle things down. This is where you probably want to go, but not secure enough to actually make it a release number.
Okay, we ask the community. Maybe we have to go to the all technical committee guys, ask to make some tests. Yeah. Yeah.
Stress tests, make sure that it's all synchronized. We didn't end up using something somewhere else or whatever.
Okay, we'll try to contact everyone. Yeah. Thanks, Mark. Okay, next presentation is by Smail Boughou.
Yeah.
Boughou. He is working with Big Field Cardiff, Big Field, at collaboration with University International de Rabat, Morocco, Mohad University, and Dublin, of course. And is about non-uniform mechanical properties material model for wing structural analysis. Please don't say.
Okay, thank you. And thank you already for rescheduling my session to here because of some challenges to join from the first day. So I'm Smail Boughou. I will be presenting this work entitled Non-Uniform Mechanical Properties Material Model for Wing Structure Analysis. It's a kind of aeroelasticity problem. And because I'm from background of aerospace engineering, so at the first time I was doing aerodynamics. Then we tried also to move to do the fluid structure interaction both in the field of aerospace engineering, because nowadays some focus group now are trying to provide some benchmark on the aeroelasticity. Mainly the American Institute of Aeronautics and Astronautics research groups, they are putting some efforts together, and some of the members maybe you have met also in some previous workshops from University of Michigan and some in Politecnica di Milano also. They have some members from this group. So I just don't want to take much time. So I will start by introduction about why we are implementing this non-uniform material model in the wings of the unmanned aerial vehicle. And I will explain some modeling steps, and I will try to give some results and discuss. So the first motivation is that looking into the flights regimes in terms of Reynolds number, if you are familiar with this Reynolds number, we can classify the different flights that we have currently in different regimes, and in which regimes we have this regime of from 10 to the power 5 to 10 to the power 6. We can see that this regime, we have the large birds are flying at this regime. And at the same range, we have the unmanned aerial vehicle, UAVs are flying at this same range of Reynolds number. So our aim is to try to design wings for unmanned aerial vehicle by inspiring some characteristics from birds, especially from the bird's wings material, especially the feather material. So from there, we try to mimic some things from the birds that we can see in your daily life, what we call the morphine concepts. That is, the wings of the birds are not a rigid structure, and so in fact they are flexible. And this flexibility is what we want to inspire for unmanned aerial vehicle wings. So you can see that the birds are morphing the wing into different scenarios. They can morph in the spanwise direction, and also they are morph in the feathers direction. Actually, if we look into the wing of the bird, we can find that the bird has the leading edge of the wing is consisted of the bone and muscle, and we have another part that is the trailing edge of the wing has these feathers. So the feather is mainly our concern, and we try to look into the material of the feather in order at the end to have some characteristics that we can implement into the unmanned aerial vehicle wing. So the flowchart is just to take some experimental data from biology and try to implement into the fluid and solid interaction. I'm trying now to implement the finite volume solvers of solids for foam, and you know already you are familiar with this solver developed by Philip Cardiff from UCD and some other researchers. And that's why I was in contact with Dr. Philip in order to, because we wanted to do some modifications within the material model, and I will explain about the material model. So normally we have to have a fluid solver to solve what we call aerodynamics, which is the flow around the wing. And the data from normally it's a steady state, so we just take the simple foam solver, and we get the developed or the converged flow field around the wing. And this data of the pressure, that will be a pressure load that will be implemented into the structure of the wing. And we will see what happened to the deformation of the wing furthermore. So first, what we do in this work is that we are not modeling the 100% of the chord length of the wing, but what we do is we model only the 60% of the trailing edge. And if you ask why, because as I mentioned, because we are mimicking the bird's wing, as I mentioned, that the 40% we can say of the bird wing is bone and muscle, and we don't have much information about what material properties we can implement in that part. So we are confident about the 60% in which we can implement the feather properties such as Young modulus and some bending stiffness characteristics that we have from the experimental biology. So you can notice that this is quite multidisciplinary topic. We can have biologists as well as fluid mechanics and solid mechanics. So it's that is what's making my task quite harder to put all of these things together. Even I'm trying also sometimes to consult people from zoology department from British Columbia in Canada and different researchers. So you can see that it's quite hard. Here I'm showing for different angles of attack, we can measure the deformation of the trailing edge depending on the angle of attack, and you can see it's by increasing the angle of attack, we can see that this wing is moving upwards in different manners. I'm showing here the contour of the displacement, and there is some part that we can consider as linear part, that is some low angles of attack, that we can see that in this figure that the deformation is quite linear, but with increasing the angle of attack, we can find there is a regime of non-linear in which we can see the deformation is quite exponential by increasing the angle of attack further after 12 or 15. And from aerodynamics perspective, we can give the reason for this as what we call the separation problem in the CFD prediction. By increasing the angle of attack, we will have problem of separation, and also even the solver sometimes has difficulties to predict this separation, what we call laminar separation bubble. Here is the second part in my work, that is what I'm calling nonlinear material model. Is that instead of implementing just one single Young modulus within the whole structure, I am looking into implementing some non-uniform materials along the feeder. And here I'm looking into the biology. Some people have done taken some data from experiments on the feeder itself. They have to find the bending stiffness along the feeder for different locations. And what I have to do in this stage is to take this data and to feed it to the solids for form in such a way, if you are familiar with the initial conditions. So I put the bending stiffness in the field, in the initial condition field, and this you can do by the SWAX for form. SWAX for form allows you to define a non-uniform volume scalar field. If you have done so. So I use the funky set field. Funky set field allows you to give the expression in terms of X, Y, and Z position, and it will generate a field, and you can put in the initial condition of your setup. And this is exactly what I do. First, I had to use the nonlinear regression to extract the function from the experimental data, and I will feed it into the wing structure material properties in such a way. So you just see that this contour is same as this, is a nonlinear regression of data that we have from the experiment, and directly I will implement to the structure as in terms of the bulk modulus K. So here is the comparison between the case of uniform Young modulus and Poisson ratio, and the other case with non-uniform K, or non-uniform bending stiffness that is just mentioned, extracted from biology, fitted to the data extracted from biology. And what we can find here is that by implementing this non-uniform model, we can really mimic what's happening in the biology or in the bird's wings in terms of deformation and flexibility, instead of just using a uniform material model of Young modulus that we even the Young modulus used here is the Young modulus of the keratin material. That is, keratin material is the material that you can find in your hair and feathers and nails and so on. So this is what I was trying to do for this work. So I think so here is the comparison of the stress. The stress is the equivalent stress between the uniform and non-uniform, and we can here give the reason of this little differences. Here is that at this part, this is for the uniform Young modulus, which is normal. That here we have the conditions. Here is the clamp. So the high stress is at this region of clamped area. But for this one, this because the bending stiffness started to decrease at this area, and at that area where the bending stiffness is decreasing, we have this high stress at this area, which is also which makes sense. So we tried to do the same two-dimensional work in three-dimensional also, but this is still an ongoing work that still have to validate, in which I had to solve the flow around the whole wing instead of just a two-dimensional one, and with considering some conditions here is that the wing here at the root is clamped, and also this the 40% here this area is also clamped boundary condition also, and also it's clamped here, and the response of the deformation you can see here is that the what we call deformation is higher at the tip of the at the trailing edge of the tip, and this work is I'm trying to extend in some three-dimensional, as I mentioned, and which is ongoing. I wanted just to show some preliminary results on this. So there's also some sections across the wing to see the deformation as well, and the conclusion of displacement in terms of the span-wise. We see that the higher displacement is at the tip, as I mentioned, of the wing here. So just as to summarize, that this work is combining fluid and solid solvers by getting benefit from some experimental biology in order to design the unmanned aerial vehicle wings. And I'm looking forward to have your questions, and thank you.
Thank you for good presentation. Any questions? I have just a curiosity. How big is the simulation? You have to run together fluid and mechanics parts in OpenFOAM. Do you have to make, let's say, a coupling between them? Do you use something?
Okay, good question. Actually, because the method here, the coupling here, I started with a one-way coupling, which is I solved the simple foam, and I get the converged state of the fluid flow around the wing that I will take and couple to the solids for foam solver. So this is an initial simulation to see the response of the solid to this data from the fluid. But next we have to do a dynamic way, which is after solving the fluid, you give us two-way. Then we go with the.
Are you using the sample code for make the coupling?
Actually, the coupling is already procedure is already existing in solids for foam. But I have seen that also some people are using precise interface to precise actually can also allow to do the coupling even with the other solvers. But now I'm working inside the solids for foam itself. Solids for foam actually only solves for the solid, but we can we compile inside OpenFOAM or a foam extent or whatever is the fork you can use. So this is it.
Yes.
Yeah, could you explain a bit about the dynamic response as controlled? Are you trying to do soaring or something?
So this is actually the step that comes after when we do the dynamic simulations. Dynamic simulations will allow us to see both response even after the solids has deformed. We go back and feed this displayed mesh from the solid to the fluid. So this way, what we call, just mentioned, two ways. This way we will solve iteratively in a two way. But what the data just I have shown now is a one way. Is that answering the question?
What is the rate?
The main objective. So actually, the main objective is to mimic the biology, as I mentioned. So I have to look at the best way to implement these material properties from the bird into the actual manned aerial vehicle wing. So it will follow some steps. So the first is just blindly implementing the Young modulus, which will not really mimic the actual distribution of the materials along the bird wing. The second part is we move to modify on the material model, as I mentioned, to make it non-uniform material model by implementing the bending stiffness or the K bulk modulus. So this is the second part. Third part, at the end, we have to get the performance, aerodynamic performance increased with the use of the flexible structure. So this is the main aim. So this is aerodynamics performance. That's why I explained at the beginning that I started doing aerodynamics at the beginning. Then while beginning into this topic of aeroelasticity, I moved also to include solids, so solid mechanics. Yeah, thank you.
Mark,
Okay, not a question, but just a comment. So you know, or other people know, if when you're setting your material properties, you don't need to use SWAC for foam. You can use expression set field, which has been put in like 4 versions ago. Expression set field, and you can give an expression to set your fields for non-uniformity. That's you can implement like an expression function. Yeah. If you're using OpenFOAM. Yeah, okay. Just because.
Okay, I understand. Yeah, I got the idea that you can use the set field inside OpenFOAM, I think. Expression set field, yes. Then I found maybe it's doing same thing as SWAC form, that you just write the expression and condition, and it will generate the field. So yeah, this is exactly what I do. Yeah. Nice. Yeah, maybe I will check it. Thank you.
okay, if there is no more question, 10 seconds to speaker.
Thank you.
I think we close this session. Thanks to everyone to attend, and have a good lunch. I think, yeah.